Okay, Assalamualaikum. Why do I start with this? Because on Monday, why do I feel that this is too close? Let's see. Okay, sorry tadi saya salah tekan pula, terdelete. Okay, anyway, on Monday, somebody sent me a question. Okay, it's not from this class, it's from the other class. Okay, she sent this at 10:49 p.m. Okay. Okay, I was falling asleep, but this is a good question. Okay, you remember last time I mentioned that to show something is a vector space, there are cases in which you don't have to show the 10 axioms. Okay, boleh dengar tak? Is it clear? Or you want me to talk louder? My sound, is it clear? Okay. Alright, so before this in class, I mentioned something like if you have, say, W is like A, B, C, A, B, C in R. If you want to show this is a vector space under the normal operation, so to show that W, which is a subset of a vector space V, this is a subset, to show that W is a subspace of V, show that W, okay, to show that W is a vector space, we just need to show that W is a subspace of V, a known vector space. A known vector space means one of those four, okay, Rn, matrices, polynomials, and function. Only if the operation is the normal one, okay, like operation of Rn is a plus, operation of matrices is a plus, operation of polynomial is a plus. As an example, you want to show W is a vector space. You can see that this is a subset of N 2 by 2, which is already a vector space. So instead of showing 10 axioms, you can just show the 3 subspace tests, because the rest is already true from being a subset of a vector space. Okay, you remember the 10 axioms. You have to show it's closed under addition, closed under multiplication, because this is might not be true, and the identity, right? The rest, like distributive law, associativity, commutativity, that is true for the whole matrices. Okay, the question that I received is something different. The operation is different. Okay, let me write the question. Given that W is a set of all pairs of real numbers, so W is a set of all pairs of real numbers of the form 1x, okay, x in R, okay, with the operation, so we have 2 operations, defined by, if you have 1x1 plus 1x2, okay, this is defined to be, you don't ask me why, because this is given, 1 comma x1 plus x2 and k, k multiply 1x equal 1kx. Okay, this is sample test 2, meaning it came from one of those tests in test 2. The question is, show W is commutative. The second one, find the zero vector in W. Okay. Now, this is just 2 questions of the whole 10 exams. Okay. This is something different in which all members, this is actually just a subset of R2. W is a subset of R2 because this is a number 1 and also X. Okay. When you draw all the points, X is always 1, but Y is all the real numbers. So these are all the points. But the addition is something different. When you add 2 points here, okay, it stays on the line, but then you add the Y component. Okay, so this means this is closed, okay, because you want it to be a vector space. This is closed. When you multiply it by a real number k, this stays at 1, but you just multiplying by the Y component by k. This is still in W. So you see, this is also a vector space. Alright, so it is closed under addition, it is closed under multiplication. Question is whether it is commutative and find the zero vector. Another good thing about this question is that to show you the zero vector does not need to be always 0, 0. Okay? If the operation is change, is different from the normal operation, the zero vector can also change, not only 0, 0. Okay? So it's a good question. Alright. Alright, okay, so if you have, for example, 1, 1 and 1, 2, right? 1, 1 here, 1, 2 here. When you add these two, 1, 1 plus 1, 2, this is equal to 1, 3, right? So you get this also over here. If you have, say, 1, 2, you multiply by 3, you will get 1, 6. Okay, so this 1, 2, you get 1, 6. So it is still in the line. Now, how to show it's commutative? Okay, so let 1x1, 1x2 in W. Okay. show, call this u, call this v, show u plus v is v plus u. Okay, so you just add u plus v is 1x1 plus 1x2, which is from the definition 1x1 plus x2. This plus is just a regular plus. Sorry, this is just a regular plus. Okay, this, because the definition is different from the normal one, that's why we're using that with a circle. Okay, and there are two ways to show this. One is, you know that you have to show it's equal to v plus u, so you can just do this. Okay, one other way is you just, what is v plus u, and then you show the equal. Sorry, this is a regular plus. Okay, you can just write like this, right? Mathematically better actually to just start from left and show is equal to right, rather than sekolah dulu at school you start with this, you stop, and you start with this, you stop, and you show they are equal, which is not that nice. So you can just start from here, okay, equal to here, and then the flip, because this is a plus, and you can separate. Okay, and this is v plus u. So it's commutative. Alright. Okay, and the other question is to find the zero vector. Okay, now you see the zero vector, the normal zero vector is here, it's not in the set, so it cannot be that one. So how do you find the zero vector? You have to remember the definition of the zero vector, yeah? Okay. Okay, now let u to be 1x and the zero vector is 1y, because the zero vector has to be inside W, and everything inside W is in this form. Okay, this is in W, this is also in W. So you have to find what is the zero vector. What does it mean by the zero vector? 0, u plus the zero vector has to be equal to u. So you just solve this, you will get 1x plus 1y has to be equal to 1x. We want to find what is y, right? So what is this equal to? This is equal to 1x plus y equal 1x. So what is y? So you equate, you get x plus y equal x, meaning y is 0. So the zero vector is actually 1, 0, right? So this is actually the zero vector, because you can check back, you add 0 vector 1, 0 to anything 1x, you will get 1x back. Okay, so this is one example in which I can change the definition of the plus and multiplication. Okay, so it's not always the normal one. Okay, okay tak? Everyone understand this? Clear, right? Okay, you want me to talk louder? Okay, I will continue. Let me move this bit to that side. What do you mean by directly multiplying by 0? To find the 0 vector, you cannot multiply by 0. Because the 0 vector means 0 plus u is u. Okay? Although the answer is the same. You are saying, can you just multiply by 0 to get the 0 vector, right? But not necessarily. The 0 vector has to satisfy this. U plus the 0 vector has to be u. Okay? Multiplying 0 by something else does not necessarily will give you the 0 vector, because it depends on the multiplication. Okay? Alright, so this is the question. Now we continue with our notes. Where do we stop last time? Okay, I think we stopped at linearly independent, right? Okay. And we stop at example 317 to decide whether linearly independent or not. So now we start with page 189. Okay. Okay. Basis of V. V is a vector space. Let S be a subset of a vector space V. Okay. S is U1, U2 until UN. Okay. Let S be a subset of a vector space V with n vectors, infinite. Then S is a basis of V if S spans V and S is linearly independent. Okay, so you have to check these two, right? And what does it mean by S spans V? Recall, S spans V if every vector in V can be written as a linear combination of the vectors in S. S spans V if every vector in V can be written as a linear combination of the vectors in S. That is, for all V in V that exists C1, C2, Cn in R, such that V is C1 U1 plus C2 U2 plus Cn U1. Okay. S spans V if every vector in V can be written as a linear combination of the vectors in S. Right? That is, for all vector in V, V small v in big V, that exists C1, C2, Cn in R, all the real numbers, such that V is the linear combination. C1, U1 plus C2, U2 until Cn, Un. So the key is to find whether there exists the Ci's or not. So this is back to chapter 2. And 2S is linearly independent if C1 U1 plus C2 U2 plus Cn Un equal to the zero vector in B implies C1 equals C2 equal Cn is 0. Okay, this is what we have seen before. So in this section, every time you have to show whether S, or you have to determine whether S is a basis of V or not, you have to show these two things. Okay, if any one does not satisfy, it is not a basis. If you want to show it is a basis, you have to show both. Okay, and you can see this is the same as this. Okay, so you will show this first, and then you just replace V with 0, then you can find all the C. Sometimes a set S spans V, but they are not linearly independent. Okay, they can satisfy one but not two. Some subset, they are linearly independent, but they does not span. Okay, we will see all different kind of examples. Okay. All right. Okay. Faham, eh? Example 318, page 189. These are all bases. Okay, number 1, S is 1 0 0 1 in R2. The second one, 1 0 0 0 1 0 0 0 1. This is in R3. Okay, we call this standard basis. You remember in the definition I said a basis. I didn't say the basis, because one vector space can have many bases. Okay, so bases, they are not unique. You can have many bases. So this is just one basis. And if you do in general, okay, 1 0 0 until n of them, then 1 goes to the second one, and then 1 goes to the third one, 1 0 until 1 goes to the last one in Rn. So n of them. So you move 1 1 1 1 1 third one until the last one. This is called the standard basis. Okay, this is easy to show that it spans and linearly independent, because if you have xy, say V is xy in R2, okay, xy you can easily write as a linear combination of C1 and C2. You can easily find, right? because C1 you just put X, C2 you just put Y. So give me like 3, 4. Can 3, 4 be written as a linear combination of this? Find C1, C2. So you can just put 3 here, 4 here. So in this case, your C1 is X, your C2 is Y in the linear combination. So that is why it's span. It's span R2. Because any V in R2 written as XY is a linear combination of 1, 0 and 0, 1. And when you want to show that they are linearly independent, when you write C1, 1, 0 plus C2, 0, 1 equals 0, 0. Okay, when you equal to 0, 0, now X is 0, Y is 0 will give you C1 is 0, C2 is 0. Or you can solve directly, you will get this imply C1 is, C2 is 0. So also it is linearly independent. Okay, so for standard basis is easy. The same thing with the rest. So this is a basis, right? Okay. The next one is the matrices. Okay, and polynomial. Okay. Now for 2 by 2 matrix, it's the same thing, but you have 4, right? So this says 2 by 2. Okay. So this is also a standard basis for 2 by 2 matrices. Because given any Y, oops, I use V, right? Given any V in terms of W, X, Y, Z, okay, you can always write this as a linear combination of these 4. You just put W here, X here, Y here, Z here. And when you equate to 0, 0, 0, 0, they are all equals to 0. So it's linearly independent. Okay. And in general, if you have M by N, okay, this one is 4, 2 times 2 is 4. This you will get M times N, and 1 is always, I cannot write in full, but there is always 1 there, and then 1 there, and so on. Okay, it can not necessarily be square, it can be rectangle. Alright, and the last one is P. So for Pn, okay, it's 1, what do I use? X or T? X squared until xn. This is the standard basis of polynomial with degree n. And how many of them? N plus 1, right? So there is 1 from here until n, and then another 1. Or from 0 to n. You have n plus 1. And now we introduce dimension. Okay, dimension of a basis, next page, is the number of vectors in the basis, right? We call it dim V. So dimension of a vector space is the number of vectors in the basis. So we will put dimension of R2 is 2, dimension 2 of them, so it's 2, dimension of R3 is 3, so dimension of Rn is n. Okay, dimension of m by n is m by n, and dimension of Pn is n plus 1. Okay. So this is example 319. Okay. Okay. Now look at theorem on page 191. Theorem 3.6 and theorem 3.7. If you have a linearly independent set with the right dimension, then it is a basis. Okay, and if you have the right number of vectors in the S and its span, then it is basis. Okay, this theorem says if you have the right number of vectors, okay, if you have the right number of vectors for the dimension of n, okay, let S be linearly independent set in a vector space where the dimension is n, then it is a basis. Okay, it means that if you know it's linearly independent, or you know it spans, then it is basis. This is just to use, but not to be given as a proof for a basis. For a basis, I normally don't use this theorem just to know whether it is a basis or not by counting, but you have to show both. Okay, I didn't really use this theorem. I normally will use theorem that says it's less than or it's more than, that is not a basis. Okay. Now, okay, this, I normally use this theorem. Let me, okay, let S equal to U1, U2, UM, right, and dimension of V is n. First case, if M is less than n, then S does not span V. You remember this when we first look at spanning, right? If it's less, then it does not span. If it is more, it might span, it might not span. It depends. The second one, if M is bigger than n, then S is not linearly independent. We have seen this also under linearly independent. If it is less, you don't know. It might be still linearly independent. You've seen in the last example. But if it is more, then definitely it is dependent. Okay? So the third case is when they are equal, then if A is not 0, then S is a basis. And if A is 0, then S is not the basis. It is not a basis because it is not both. Okay. What is A? A would be the matrix in which the vectors can be formed as the column. Alright? You have seen this before. So I normally don't use this theorem but I will use this to decide whether it is a basis or not. You cannot just mention yes it's a basis or no because just M and N, okay? Because you have to show these two. Every time you have to determine it's a basis or not, you have to show these two. Otherwise you will lose your mark. What do you mean by 4 bigger than 3? Then how do you relate and so on? Okay, so this one is on page 191, yeah? Okay, look at more example. Example 320. Okay, 320. Determine whether it's a basis or not, right? If the question is determine whether, you have to answer at the end yes or no, right? If not, then you will lose the answer, the mark for the answer. Okay, so number 1, S is 1, 2, 1, 2, 9, 0, 3, 3, 4. Okay, in R3. Okay, now how many, what is M? M is 3, N is 3. So it falls here, right? So you can check also. But to determine whether it's a basis or not, they check whether S spans R3. Because there's points for writing this out, okay? That is for all x, y, z in R3, there exists C1, C2, C3 in R, such that x, y, z equals C1, 1, 2, 1 plus C2, 2, 9, 0 plus C3, 3, 3, 4. Okay, so you have to come up with this. How do I know it's x, y, z? Because it's R3. How do I know C1, C2, C3? Because there are 3 of them. Okay, and then you multiply by this. This gives the coefficient matrix A 1, 2, 1, 2, 9, 0, 3, 3, 4. Right? And system of linear equation like this. And you remember we want to see whether C1 that exists or not, C1, C2, C3, right? This goes back to chapter 2. solving system of linear equation, you can use Gauss-Jordan or you can use the determinant, right? Because in this case, m is equal to n. Okay. If you solve this, you will do row reduce, right? So I've shown it. I'm not gonna write it again, but on page 193, I've written this, and you reduce until the end. You get the row reduced echelon form. Okay, and then you get C1, C2, C3. Okay, that is one way. It's a long way. A short way will be find the determinant. Okay, the determinant turns out to be -1, which is not 0. Okay, thus there is a unique solution. So Ci exists, thus S spans V. This is by using the determinant from chapter 2. Because if the determinant is not 0, there is a unique solution, so it's spanned. The problem occurs with this if it is 0 and you need to find the spanning. You cannot find it by using this. So you row reduce. If you remember last time we did example, at the end you get 0, 0, 0 and something with x, y, z. That is the span. So if you have to find the span, you need to do row reduction. Okay, in this case, because this is unique, right? Then it's span. Okay. Now how to show it's linearly independent? Also, for linearly independent, you just replace x, y, z with 0, 0, 0, right? 0, 0, 0. And since the determinant is not 0, unique solution in homogeneous system, meaning they are all equal to 0. Alright, so in that case, it's also linearly independent. You go through the example, okay, because I've given the whole answer in there. We go to number 2. So don't forget to show it's linearly independent. Okay, I will write here. Okay, this is a little bit different. You don't write like this. You write you have to write this. This equal to 0, 0, 0. Does it imply Ci is 0 for all I? Okay. Then you will write again like this. Okay, the determinant is not 0. There is a unique solution, meaning all Ci is 0, so S is linearly independent. Thus, S is a basis. This is the final answer. Don't forget to write the final answer. It is a basis. Okay, we go to number 2. Determine whether it's a basis, yeah? If you remember the theorem, you will easily know whether the answer is yes or no. 101 and 110. Okay? Now, I know the answer is no, because it's not enough, meaning it does not span. Okay? But you cannot just say m is 2, n is 3, 2 is less than 3, so it's not a basis. You cannot write like this. Okay, so show S does not span R3. How do you show this? S spans R3 if you can find, let me write, S spans R3 if for all x, y, z in R3 that exists 2 only in R such that x, y, z equals C1 101 plus C2 110. Okay, so again you write 101 110 x, y, z, right? Then you can do once, negative R1 plus R3, get 11x, 01y, 0, negative 1, negative x plus z, one more, R2 plus R3, then you will get 11x, 01y, 0, 0, you add, right? Negative x plus y plus z. Okay, it's also in the book, but yeah. Okay. I just mentioned that show this is inconsistent, yeah? So this one you have to show. Okay, so thus the system is inconsistent. Thus, there does not exist C1, C2 in R, right? So S does not span R3. Does not span R3. So what is the answer? S is not a basis of R3. This is the final answer. And why it is not a basis? Because it does not span R3. You know R3 is like this, right? X, Y, Z. This is a surface, a plane. So since it's only 2, it only spans a plane. And if the question asks you what is span S, okay, what is span S? We have done this before. Span S is equal to x, y, z in R3, negative x plus y plus z equal 0. This is a plane, right? Or y equal x minus z. It's a plane, so it does not span the whole R3. So that's it. If the question asks you to decide whether this is linearly independent or not, then you have to find it. If you have found the span, it's easy to find whether they are linearly independent or not. Because to check whether S is, this we know is already not a basis, but just to check whether S is linearly independent or not, first you remember the theorem last time, there's only 2, one is not a multiple of the other one, so we know it's linearly independent. But trying to use the definition, it's linearly independent if you have 0, 0, 0 equal C1 U1 plus C2 U2 implies C1 is C2 is 0, right? So in that sense, we already have this. So when you replace 0, 0, 0 here, x is 0, y is 0, z is 0, you will get also 0, 0, 0. And from that you will get, so you don't have to do everything again. You just replace x, y, z equals 0, you will get right? So there is a C1, C2 here. So C2 is 0, put in here, or you can do another row operation, right? So C2 is 0, put in here, you get C1 is 0. So C1 is C2 is 0, so yes, it is linearly independent. So in this case, although it's linearly independent, it does not span, meaning it is not a basis. Okay, so this is what you have to do for this question. Move on to number 3. Example 320 is very similar to number 2. Okay, now there is another type of question that asks you to extend to be a basis. It's not enough. How can you extend to get a basis? So that is why there is another part, page 195. Okay, to add another one, we need another one to extend to be a basis. Okay, so extension of a basis. If it's not enough, how do we extend to be a basis? The problem here is that the answer is not unique, right? Because you can add infinitely many third vector to get a basis. So my suggestion will be add one from the standard basis if it is not already there. Okay, 1 0 0 or 0 1 0 or 0 0 1. So if it is not enough, in my notes I add this, the third one, and then you can check the determinant, right? Determinant, take this one, right? Take this one, determinant is -1. So the determinant is -1, not 0, so this is a basis. Okay, so that's one way. If determinant is 0, probably you need to add another one, 0 1 0 instead, or 0 0 1. Okay, so that is how you extend to be a basis. For number 3, you have 1 0 1 0, 1 -1 1 -1. Okay, again it's very similar. I know this is linearly independent because it's not a multiple. I know it does not span R4 because it's not enough. It has to be at least 4. So you have to go through the same process. Okay, but to extend, you need at least 2 more. Okay, you need at least 2 more. Okay, you need at least 2 more. The problem is, what happened when you add, the determinant becomes 0. So which one that you want to add? So my suggestion is, you just add all, and then you reduce. The column that you have the leading one is the column that you will choose as the basis. Okay, so this is easy. Just add all and then reduce, and see in the row reduce, take the leading one for each row, choose that column as your basis. I think I did that on number 3. Let me see. Yes, page 196. Okay, when I do this, I get 1 0 0 0 1 1 0 0 1 0 1 0 0 negative 1 0 1 0 0 negative 1 0 0 0 0 negative 1. Okay. Okay, so this is already row echelon, right? It's not row reduced, but it is already row echelon. So from this one, you can choose the first 4. Okay, 1 2 3 4. So this becomes the basis. You add these two. Okay, sometimes it skip this one, it go to the next one, the next column, so you will choose the right column. So this is the way to add until it is a basis. Originally it is not, because it does not span. Yeah, that is number 3. Number 4 is similar. Okay, number 4, it does not span because 2 is not enough. Last question is a little bit different, because last question it's more. Okay, S is 1 1 1 2 2 2 in R. Why is it R2? Because 2 component. Although this is 3, but each one is 2, right? So it's R2. In this case, M is 3, 1 2 3, but the dimension is 2. Okay, so in this case, it's too much, meaning I'm not sure whether it's span or not. You have to check. Okay, because M bigger than N does not necessarily mean it's span. You didn't say, but definitely it's not linearly independent. So I know it is not a basis because it is not linearly independent. Okay, you can go direct to showing linearly independent, but if the question asks also whether it's span or not, then you can also show that. Okay, now let me show both. Yeah, S spans B if for all x, y in R2 there exists C1, C2 in R such that x, y equal, sorry, there are 3 of them, C1 1 1 plus C2 1 2 plus C3 2 2. Okay, now we do this 1 1 1 2 2 2 x y. Okay, so negative R1 plus R2. 1 1 2 0 1 0 negative x plus y. So you will see that this is consistent, right? C3 is free, but the system is consistent. The system is consistent. Thus, C1, C2, C3 exists. Many solutions actually. So, S spans V. If I ask you a trick question, what is span S? If you look at here and I ask you a question, what is span S? Type. I want to see your answer. Cepat bagi jawapan. Okay, what is span S? Okay, so span S is V, which is R2. Because we have shown that S spans V. Okay, S spans V means span S is actually V is the whole R2. Alright, sometimes they just ask this actually right away from this one. Okay, the second part is whether it's linearly independent or not. Right, so for the second part, actually the different thing is that, okay, you don't have to have this, okay. S is linearly independent if C111 plus C212 plus C323 equals 0, 0, 0. This is a must, yeah? You have to write it equal 0, 0, 0 implies C1 equals C2 equals C3 equal 0. Okay? And when you put this, okay, when you put this will be, okay, terlebih satu pula. Sorry, 0, 0, yeah? Because it's R2, okay? And, okay. So, you will get this. What is, this gives what? This gives C3 is K. Free variable, right? C1 is not free, C2 is not, C3 is free. So, when C3 is K, meaning not all Ci is 0. Okay, thus S is linearly dependent or S is not linearly independent. Right. Therefore, S is not a basis of R. Okay, actually this is not difficult if you really understand what you should show and you really understand what it means by the linear combination and also system of linear equation. Yeah. All right. Okay, so we finish example 320. Okay. Let's try some question. In my next class, I will go to coordinate vector and change of basis, because that is actually just continuation of this. There's nothing new. It's just once you get this, you just rewrite. That's it. So not something new. The next section is, okay, I forgot to charge my laptop. All right. Okay, so the next section is row space and column space of a matrix. It's just reduce matrices, and then you will get the row and column space. Okay. Right. Orthogonal and orthonormal set is the Gram-Schmidt continuation of chapter 1 when you have the orthogonal matrix. We change a little bit. That's it actually for chapter 3. Okay. Then we'll have our test 2. I will update once we, according to what it is now, we have the date already for test 2. We will do it online. We'll give you the question at that specific time, at that specific date, and then you will write your answer and then you email to us. That is most probably it, right? For 1.5 hours. Okay. Any question? Okay. Now let's try some question, yeah? Last time you did 20 to 23, right? Okay, let's do this. Actually, I want to reduce giving you assignment because I have to return the assignment for your test, so I don't want to give you more. Try exercise number 24. Linearly independent. One is 2, one is 3. Six. For next class, this one is now, yeah? I'll give you like maybe 5 minutes, 10 minutes. I have to stop like 3:50. Okay. This is for next class. If you can try this, then we will discuss this. 24, 26, 30. Okay, and then basis. Then I will explain 40. I have not given you anything about 40. Okay, try it in 8 minutes. Okay, last time I asked you to try 24 to 36. Ya ke? 24 to 36? No. Belum ajar takkan saya suruh. Last time I said 20 to 23, right? Any question? 20 to 23. Yeah, last class 20 to 23. So, is it okay? Do you get 20 to 23? Any question from those? I will explain if you have any question. Okay, that's the question 23E. Is that the only one? 23E, yeah? Okay. Whether the set below span are okay. Now I see the problem is it's supposed to be R2, right? So for 23E is actually R3. Okay, that is not supposed to be there because the question is determine whether the set below spans R2. So I had to scrap E because E is actually for R3. But for R3, the answer would be yes. One, two, 1, 1, 0, 0, 0, 0, 1, right? Because this one, the determinant is -2. So it spans R3 but not R2. Thank you for pointing that out. Any question for 2023? Okay, 22, is it in the span? It is in the span if it can be written as a linear combination. Alright, number 22. The vector is in the span if you can write it as a linear combination of the others. That is the easiest. If you show already the set S span the whole R4, then also there is another way to do that. Okay, for number 24, okay, 24A, is it linearly independent? The answer is no. Right? No, not linearly independent. You see there is a 0 vector there, right? So if you put C1 1 1 plus C2 0 0 equals 0 0, then this does not imply C1 is C2 is 0, because you can do this, right? This is not 0, but the rest all equal to 0. You did this last time. For B, no, because you have 3 more than 2, but again you can solve this. 1 2 3 1 4 2, right? 0 0. By chapter 2, reduce once more. You can find many solution meaning not all 0, because we want a unique solution, right, for to be independent. 26A, you can see the determinant, right? Okay, 26A, you can find the determinant. Unique solution means all CI is 0, so linearly independent. The second one you have to check by solving, because it's less. Okay, if it is less, you have to check. So if you check, you get 1 0 2 1, 1 0 6 2, 2 0 8 3. Okay, reduce this. This is already all 0, you can put it down there. So check this, whether unique or not. If it is unique, can it be unique? Probably, right? Because there is a 0 here. If it is unique, the answer would be yes, linearly independent. Alright, so this is 26. Which one is this? Oh, this is 25, sorry. Salah salin pula. This is 25, yeah? Wait. This is 25. I want to do 26. Okay. 26 salah salin. 26B, yeah? Okay. Alright. Okay. For this one, you have to check, because this is 4 by 4. Right? You can find the determinant also for this one. If the determinant is not 0, right, then the answer is unique. So it's linearly independent. Okay? That's 26. 30. Okay. Yeah. Next class is 33. 30. I just do 1, then you can see 1 and x. Okay, this is for P1, right? 2. So when you do this 1 and x, you will do 1 0 0 1. So this one is okay, huh? This one is okay. If you want to put px in terms of a1x, a naught plus a1x. Okay, the v that we used before is in terms of this. Alright, don't put x inside the matrix. Okay, you will put here a naught a1. Okay, so this is linearly independent. Also for spanning, when you want to do spanning for polynomial, when you write for v equal px equal this in P1, then there exists and so on. And the vector has to be in the form of polynomial, right? So what you put in here is the coefficient, not the x. The x stays there. And this is the C1, C2. So in this case, you will see that the solution is unique. Okay, for independent, yeah. Okay, so for independent, this is for spanning. For independent, you will always put 0 0. Okay, so the answer is yes. Okay, for B you have 3. Okay, B you have too many, so has to be dependent. C, yes. Okay, independent. D, you have to check. But D, -2, -2, 1 1. This is also the determinant is 0. So for this case, it's dependent, yeah. 30D. Okay, I'll go to 37. Basis of R2 or not. Two, 4, and 3, 6. Basis of R2 or not. So you see this, if you see the determinant is actually 0. Okay, so I know this is not a basis. Okay, so for spanning, it does not span. This is a little bit tricky because then you will -2 R1 plus R2. I do this first because I don't want fraction. -2 plus, right? So I can just leave it this, but you can just also put 1. This is also already, we know inconsistent, so does not span, right? So this is 37. And the other one is 1436, yes. Okay, this one, the determinant is not 0. Okay, you can do this. So it is a basis. Okay, then I go to last one. Yes, time for 40. You are given S equal, the first one, I think, let me check first. 2, 1, 3, 1, 2, negative 1, 1, 0, 2. What is the determinant? Anybody did number 40? Eight. 9 minus 1. Right, and then 0, and then minus 6, and minus 2. It's not 0, right? Determinant is not 0, it is a basis. Is it? Let me do this. 2, 1, 3, 1, 2, negative 1. 1, 0, 2. Okay, put like this. 8, 0, minus 1, minus 6, 0, minus 2 kan? 7, 1, negative 1, it's not 0. So, part A, S is a basis. Okay, S is a basis of R3. So span S is R3. Dimension of span S is 3. Find a basis and dimension for span S. So since S is a basis for all of R3, span S is R3, right? The whole S is a basis, dimension is 3. For part B, you see part B, there are more than 3. There are 4. So you have to get rid of 1. Okay? So you have to do this. 2, 1, 3. 1, 2, negative 1. 1, 0, 2. 1, 1, 3. Okay, R1, R2, 1, 2, 0, 1, 2, 1, 1, 1, 3, negative 1, 2, 3. We want to find the row, the column with leading 1. Negative 2, R1 plus R2, negative 3, R1 plus R3. Okay, 1, 2, 0, 1, 0, negative 3, 1, negative 1, 0, negative 7, 2, 0. Okay, teruskan. Then you get 1 here. Then you get 1 here. Teruskan ya. And then you will choose the first 3. So the first 3 is the basis. If you don't like fraction, instead of multiplying this 1/3, you can multiply this by 2. You can multiply this by -2. Then you add, then you will get 1 without any fraction. Panjang sikit lah. Okay, so reduce this. Then if you have 1 here, 1 here, 1 here at the end, so these 3 will give you the basis. Okay, if I close this, okay, if I take just these 3, okay, you find the determinant is not 0 kan? 8 minus 1, sama dengan tadi soalan dia. Oh ya, tak perasan. If you take the first 3, this is exactly part A, right? So this is the basis. Okay, so you have to write for B as the first 3 is the basis for span S, and dimension is 3. Okay, span S is actually R3. I can give you another question with macam ni. I can give you U1, U2, U3, U4, in which when you reduce, you get only these 2 as the leading one. So in this case, the dimension will be 2, and the span is just like before, a plane. It's not the whole R3. Okay, so I can give you something in R3 terlebih, but then when you reduce, you have only 2 left as the leading one. Maybe you will get something like 1 0 0 0 1 0, and then the rest semua 0 macam ni kan. So then you take just the first 2, only 2. So span S is just span of these 2, a plane, dimension is 2. Okay, so but in this one, dimension is 3. Okay, so now you can try and do until 47. You don't have to hand in ke apa, but you should discuss in your group. Okay, make sure that you get the same. You do it yourself first, and then you should communicate and discuss in your group and make sure you get the right answer. Alright, until number 47. In the next class, we will continue. If you have any question, let me know. We will continue with the next section. We have like sikit je lah, sikit lagi. It's just the coordinate vector. It's just by putting in the coefficient, and also row space, column space. We've been doing this, just the definition, and Gram-Schmidt process is just a formula. Okay, it's toward the end of chapter 3. Alright, faham ya? Okay. I have another meeting at 4, so those who did not yet scan the QR code, semua dah so I can see that everyone dah dapat attendance. Okay, which is good. Okay everyone, bye. Nak kata enjoy at home, you are already wherever you are, but enjoy the weekend. Bye. Make sure you like the video, yeah. Only 51. Stay at home, guys. Wherever you are, jangan jalan-jalan, nanti kena tangkap. Okay, ending. Finished. Bye.